Modern computers run thousands of processes, active tabs, and background applications simultaneously. Every single one of them needs physical space to exist and execute. The CPU processes data at billions of cycles per second. But despite that raw computational speed, the CPU cannot independently manage where every byte of data physically lives. That data is held in main memory, or RAM. It acts as a shared repository constantly accessed by the CPU, but it is entirely volatile, meaning it instantly loses its contents if the system fails or loses power. If all those running programs directly grabbed physical space in the RAM, they would inevitably collide, constantly overwriting each other's data and crashing the machine. This documentation shows how the operating system solves the problem. The OS takes on the strict responsibility to keep track of which parts of memory are actively being used, and by whom. By tracking every allocation, the OS can safely manage process suspension, resumption, and synchronization without causing hardware-level conflicts between competing programs. Without a strict manager acting as a barrier, the raw processing power of the CPU would quickly corrupt the entire system. The system requires an invisible abstraction layer. To prevent these collisions, the CPU is fed an illusion. When executing a program, the CPU believes it has access to a continuous, dedicated block of memory entirely to itself. This defines the mechanism behind the illusion. The address generated by the CPU for every active page is the logical address, a completely abstract coordinate. Contrast that with the physical address, which is the actual hardwired frame in the hardware where data is permanently stored. This creates a structural disconnect. A process's logical addresses might be perfectly sequential, counting up step by step, while its physical addresses are scattered across entirely random, non-contiguous frames in the RAM. To resolve this disconnect, the operating system relies on a specialized hardware component, the Memory Management Unit, or MMU. The MMU acts as the system's translator. It ensures the CPU's abstract requests land precisely in the chaotic reality of the physical memory hardware. Let's trace the exact journey of a single memory access request generated by the CPU. Out of millions of instructions, we isolate one specific logical address. This address is not a single coordinate. It is a compound structure, split into two distinct parts. As detailed here, the first segment is the page number. This mathematically represents the specific logical chunk of memory the CPU requires. The second segment is the offset. This represents the exact byte location nested deeply within that specific page chunk. Natively, the CPU only understands these logical pages and offsets. It knows absolutely nothing about physical hardware frames. Standardizing all memory requests into this strict two-part structure provides the mathematical baseline required to make hardware translation possible. That separated logical address now physically enters the Memory Management Unit. According to the documentation, the MMU has a singular directive. It must convert the logical address into a physical address by translating the abstract page number to a physical frame number. The MMU accomplishes this by referencing an internal tracking map called the page table, maintained by the operating system. It looks up the logical page number, revealing a new physical frame number. This complex lookup process takes a fraction of a nanosecond, running entirely invisible to the active program. This newly generated frame number is the true coordinate. It points to the exact physical block in the RAM hardware where the page data resides. The OS page table operates as the master ledger, the sole entity mapping the CPU's abstract requests to true physical locations. But we still have the second half of our logical address, the offset, which has remained separated during the page translation. The architecture relies on a critical rule of paging. The MMU leaves the offset mathematically untouched throughout the entire translation process. While the page number is entirely stripped and replaced by a frame number, the relative location of the byte within that chunk remains identical. The new frame number slides next to the original offset, merging to form a complete physical address. This initiates the final execution step. The newly combined physical address transmits across the system bus directly to main memory hardware. The RAM receives the physical coordinate, locates the exact frame, targets the correct byte using the offset, and sends the raw data back to the CPU. By isolating the translation operation entirely to the page number, the architecture guarantees a highly efficient, mathematically non-destructive path to data extraction. This microoperation solves a massive problem, balancing the CPU's endless demands against physical hardware reality. The hardware poses an absolute constraint. As defined here, physical address space is strictly limited by the actual size and number of frames available in main memory. This OS documentation outlines why the system must strictly track these frames. Without careful management, process demands would quickly overflow the available hardware space. Paging circumvents this. It enables the OS to take a massive application, break it down, and load it into non-contiguous physical frames scattered across the RAM. As physical space fills up, the system seamlessly swaps inactive pages out to the hard disk, making room to pull active pages in. The rigid limits of the motherboard's RAM are neutralized by the MMU, mathematically mapping those fragmented pages on the fly. The CPU requires absolute order and sequential continuity to process code, while the physical RAM is a finite, highly fragmented resource. The memory management unit's split translation of page and offset operates as the invisible bridge connecting these two conflicting realities. This abstraction provides total structural security, physically preventing isolated processes from discovering or overwriting another program's memory space. Logical addressing provides the foundational architecture, allowing modern operating systems to multitask safely, efficiently, and endlessly.